Depends on the time you are watching this. The subject is Engineering Mathematics 4, MEE 362, Part 2. Professor Ahad Zubair is my name. I will be taking numerical analysis, and these are lecture 1. I posted a book on the platform. Let me now share the book with us here. I hope you are seeing my screen. This is the book is on numerical analysis. The book is on numerical analysis. Okay. Okay. I hope the screen is clear. This is the book, Numerical Analysis, G. Shankar Rao. We will eat as much as possible parts of this book. By the grace of God, let's dive into chapter 1. Chapter 1 is on errors. So there are two kinds of numbers. You are going to read a lot of it on your own. I just want to scan through this chapter with you. There are two kinds of numbers. You have what you call exact number, and you have the approximate number. An approximate number x is a number that differs, but slightly, from an exact number x. So small x is the approximate, capital X is the exact number. For example, the numbers 1, 2, 3, 3/4, 3/5, they are exact number. Pi, comma, square root of 2, exponential are also exact number. But when you write 1.41, it is an approximate value of root 2. 1.414 is also another approximate. Similarly, 3.14, 3.141, 3.14159, they are approximate values of pi. Significant digits. The digits that are used to express a number are called significant digits. Figure is synonymous with digits. Definition 1, a significant digit of an approximate number is any non-zero digit in its decimal representation, or any zero lying between significant digits, or used as a placeholder to indicate a retained place. So the digits 1, 2 up to 9 are significant. 0 is also a significant figure, except what is used to fix the decimal points or to fill the places of unknown or discarded digits. For example, 0.000 5010 are not significant. The first 4 zeros, they are not significant, since they serve only to fix the position of the decimal point and indicate the place values of the other digits. The other 2 zeros are significant. 2 notational conventions which make clear how many digits of a given number are significant are given below. 1. The significant figure in a number in positional notation consists of all non-zero digits and 0 digits which one lie between significant digits, lie to the right of decimal points, and at the same time to the right of a non-zero digit, are specifically indicated to be significant. The significant figure in a number written in scientific notation, n times 10 raised to power n, consists of all the digits explicitly in m. Significant figures are counted from left to right, starting with the leftmost non-zero digits. Examples will convince us. So when you have 37.89, we have 4 significant digits. 5090, we have only 3. 700, we have 3. And so on and so forth. Rounding off numbers. In order to round up a number to n significant digits, drop all the digits to the right of the n significant digit, or replace them by zeros if the zeros are needed as placeholders. And if this discarded digit is less than 5, leave the remaining digits unchanged. Greater than 5, add 1 to the last retained digits. You will be reading line by line. Where I will only scan. Example 1.2, 0.522, whatever. So the significant, if we are looking for 3 significant digits, when we round up, it will be 0.522. If it is 4, it will be 0.5223, and so on and so forth. So for example here, we can see here that if we want 3, it will be 93.2. If we want 4, it will be 93.22, because the next digit is 5. It should not be difficult for us to grasp. If you are giving specific examples, specific number, 4 significant figures, this will be your results. Now, errors. One of the most important aspects of numerical analysis is the error analysis. Errors may occur at any stage of the process of solving a problem. By the error, we mean the difference between the true value and the approximate value. So error equals true value minus approximate value. Types of errors. Inherent errors. These are the errors involved in the statement of a problem. When a problem is first presented to the numerical analyst, it may contain certain data or parameters. If the data parameters are in some way determined by physical measurement, they will probably differ from the exact values. Errors inherent in the statement of the problem are known as inherent errors. We have analytic error. These are the errors introduced due to transforming a physical or mathematical model into a computational problem. Once a problem has been carefully stated, it is time to begin the analysis of the problem, which involves certain simplifying assumptions. The functions involve mathematical formulas are frequently specified in the form of infinite sequences or series. For example, consider sine x equals that. If you compute sine x, this will be the exact value. Whereas if we use this series to compute sine x, we only use some of the terms, then error is going to be introduced that leads to an error. Similarly, what are we saying here? If you compute sine x using your calculator, we are looking for sine pi over 3 radian. Type on your calculator sine pi over 3, you get some figures. Now enter here pi over 3 minus pi over 3 cube over 3 factorial plus pi over 3 raised to power 5 over 5 factorial. When you compute this, there's going to be error because you are not using all the terms. If you can use all the terms up to infinity, there will not be error. But when you short, there's going to be an error. So the value you are going to get there is going to be different from the actual value of sine x. That error is known as analytic errors. Round-off errors is the next error. When depicting even rational numbers in decimal system or some other positional system, there may be an infinite, if there may be an infinity of digits to the right of the decimal point, and it may not be possible for us to use an infinity of digits in a computational problem. Therefore, it is obvious that we can only use a finite number of digits in our computations. This is the source of the so-called rounding errors. So we have 3 types of error. We have an inherent error, we have analytic error, we have round-off errors. By the error of an approximate number, we mean the difference between the exact number x and the given approximate small x. It is denoted as E or by delta. E equals delta equals x minus small x. An exact number may be regarded as an approximate number with error 0. That's good. The absolute error of an approximate number x is the absolute value of the difference between the corresponding exact number x and the number small letter x. It is denoted as E subscript A. So in this case, when you have absolute error is different from the error. For example, your error, the exact error can be minus, can be plus, but the absolute error will not be plus. The limiting error of an approximate number denoted by delta x is any number not less than the absolute error of that number. That's error. So if the error is less than delta x, it means our exact number will be x minus delta x or x plus delta x, which can be written like this. So ladies and gentlemen, I want to believe that this chapter is readable and you can continue to read it. Definition 5, done. Definition 6, done. When I say done, I hope you know what it means. Definition 7, done. That means go and do it. Section 1.5, relative error and the number of correct digits. Relationship between the relative error of an approximate error and the number of correct digits. Any positive number x can be represented as a terminating or non-terminating decimal as follows. Okay? Where sigma 1 are the digit of the number x, and sigma m is not equal to 0, m is an integer. For example, 1734.58 is going to be equal to 1.10 times 10 raised to power 0, that times 10 raised to power 10, plus 7 times 10 raised to power 2. Okay, sorry, it's 1 times 10 raised to power 3. The first thing there is 1 times 10 raised to power 3, plus 7 times 10 raised to power 2, plus 3 times 10 raised to power 1, plus 4 times 10 raised to power 0, plus 5 times 10 raised to power minus 1, because there's a decimal point there, plus 8 times 10 raised to power minus 2, and that will continue. Now we introduce the notation of correct digits of an approximate number. If absolute error of an approximate number does not exceed 1/2 unit in the nth place, counting from left to right, then we say that the first n significant digits of the approximate number are correct. If x denotes an approximate number as represented by equation 1, taking the place of an exact number x, we can write that EA equals x minus x is less than half times 10 raised to power m minus m plus 1. For example, if x equals 73.97 and the number x equal to 74 is an approximation correct to 3 digits. Correct to 3 digits. That means EA, which is 0.03, is less than half raised to power 10 raised to power, is half times 10 raised to power 1 minus 3 plus 1. Where did they get this from? Since we are, from that formula, it says m minus n plus 1. In this case, since m, the place where we are approximating, m is what? Hello, this is 73.97. It is the third location that we want to approximate. It is the third location that we want to approximate. So if that is the third location, which means m is equal to minus 3, then plus 1. Let's see what they are writing here. You see, when you are reading this book, you have to take your time to follow it. They say that in this case now, m minus n plus 1. What is m? If the absolute error of an approximation does not exceed 1/2 unit in the nth place, counting from left to right, then we say that the first n significant digits of the approximate number are correct. So the error is going to be less than 10 raised to power m minus n plus 1. We have alpha m minus 1, alpha m minus 2, alpha m minus n plus 1. Let's move up a little bit. The way you interpret your number is this: x equals to alpha m 10 raised to power m. alpha m minus 1 10 raised to power m minus 1. So in this case, m, our m in this case, since we are having our m is going to be 1. I'm coming, please. Sorry, ladies and gentlemen, you take time to reason between the example, between what you are told before. This is alpha m 10 raised to power m. So in this case now, you know that this 7 is 10 raised to power, this is 10 raised to power 3 times 10 raised to power 0, 3 times 10, 7 times 10 raised to power 1. So our m is actually going to be 1. That's why they wrote 1 here. Our m is going to be 1. And then, what is n? N, if the absolute zero of an absolute number does not exist, in the nth place, the nth place, which we are going to use here is that the nth place in this case is going to be the third, because we want to approximate the third. That means we're actually coming into two decimal place, two significant figures. So we are approximating the third. So that third, n is going to be 3. So that's why they now wrote that half 10 raised to power 1 minus 3 plus 1. So, and then the absolute error is going to be less than 0.05. 0.05. If n is 3, if n is 3, I think it is the fourth. 1, 2, 3. Okay, another example will come. Let's see if there's another example there. I want you to know how to get this 1 minus 3 plus 1. Let's look, maybe that if a positive number x a correct digit in the narrow sense, the relative error, okay, let's look for an example. An example illustrates things better than the grammar. Let's look if there's going to be another example. Read all this. Let's look for examples. You may not remember the rules, but you should remember the examples. How many of these are to be taken in computing 20 so that the error does not exceed 0.1%? 0.1%. The first digit of 20 is 4. So alpha m is equal to 4. Get us, what's the root? Somebody, please, one of you get us, what's the root of, give me a Bible there. What's the root of square 20? Give me a Bible there. What's the root? Okay, is actually 4.472135,955. So the square root is actually 4.472135. They want the error to be less than 0.1%. Can you help me get the 0.1% of that figure? What's 0.1%? You multiply that by 0.1 and divide by 100. That's what it means. Multiply by 0.1 and divide by 100. You're having it as 0.0044472. Okay? Now, so which means if you want the error to be less than 0.1%, that means the error has to actually be less than 0.004. Now, it's saying that 1 over alpha m is 4 times 10 raised to power, if we are using the 4, 1 over alpha m is going to be 1 over 4 times 10 raised to power 4 minus 1, which is less than that. N is greater or equal to 4. One square root of 20. We said it is 4.47213595. We're looking for an error that will be less than 0.1%, which means our error must be less than 4.this times 0.1 divided by 100. We got that to be, our error should be less than this. So if that is the case, what approximation can we do that can make our error to be less than that? Since we are having 2 here, if we lose these 2, we're having 2 here. If we lose these 2, the error is going to be greater than that. Or if we lose this 1, the error will be less. So I think if we can approximate to 4 significant figures, the error cannot, if we approximate to 4 significant figures, what would then be the error? The error will be like this. The error will be like this. Let me copy that. The actual error will then be paste. The actual error will be 0.00 because hello. So the actual, if we can cut this away, this is what we are cutting away, definitely it's going to be less than this. The error here is going to be less than that because 0.001, 0.004. So which means the best thing to do is to do what? Is to approximate to 4 significant digits. Let's now see how he evaluated it. Let me stop sharing that one. Let's go back to our book. Let's go back to our book, which is this. So he now said that 1 over alpha m is 4. 1 over alpha m is 1 over 10 times 10 raised to power n minus 1, which is 4 times 10 raised to power 4 minus 1 must be less than 0.001. So n should be greater than or equal to 4. Well, the formula that he has used is not that clear, but at least by the analysis that we have done, I think we are good to go. Example 1.5, x equals 8 over 9, and the exact decimal representation of x is 0.088. 35 root 1 numerically when x is rounded off to decimal digits. The decimal representation of x rounded up to 3 decimal digits is 0.889. Then EA is going to be 8 over 9 minus that, 8 over 9 minus that. And what are we having? We're having that EA is 1 over 2 multiplied by 10 raised to power minus 3. (1.5.2) Tables for determining the limiting relative error from the number of correct digits and vice versa. Relative error in percentage of numbers correct to n digits. If first two significant digits, if that is 10, then we will need that's 2 significant digits. Okay, let's go through this. So please go through 1.6. So please, you are not supposed to memorize formulas, but you should be able to concentrate. Don't memorize formulas, please. Use the example to guide you. Example here, they say round off 27.8793 correct to 4 significant figures. So that will become 27.88. Round up this number to 4 significant figures. That becomes 0.002435. Okay. Find the sum of approximate numbers. This each correct to the indicated significant digits. So I think you can follow this example on your own. Example 1.9. Find the number of significant figures in the approximate number 11.2461, given its absolute error as 0.25 times 10 raised to the power minus 2. Given the absolute error as that, which is equal to that, the number of significant figure is 4. Number of significant figure is 4. So what did they get at the end now? The number of significant figure is 4. Write the number of significant figures in the approximation number of this, giving its absolute error as 0.25 times 10 raised to the power minus 2. So the absolute error is 0.0025. That means it must have been approximated to 4. 1, 2, 3, 4. Okay. Now, let me see if I can now leave you to cover this chapter. Example 1.10 done. Example 1.11 done. Example 1.12 done. When I say done, that means go and do it. Let's just count through. You should be able to go through this chapter. Example 1.1 is saying you are giving the exact number. It's rounded up to 4 significant figures. give us the absolute error, give us the relative error, and give us the percentage error. Exercise 1.1. With this coming to exercise 1.1 now, I think we can conclude that we have come to the end of this chapter. So, ladies and gentlemen, please, I want you to follow this chapter. I've only scanned through. What did I say? I scanned through. You are not supposed to scan through. You are supposed to take your time and go through. Thank God we have answers to the work examples. So we have answers to the work examples. So this will be the end of our first lecture. We have what this lecture is all about is about error analysis. Let me take us to the beginning of the chapter again. So this chapter is about errors. It's about errors. I think we can stop here. So you are supposed to go through this chapter that it is readable and then follow the examples. I don't expect you to memorize formulas. The formulas are just there to guide you. I expect you to be able to work. And fortunately for you, all the work example there, they gave you solutions. Don't memorize, try to see how they got it. So, and like we have divided it into groups, we expect you to study in groups, do tutorial together. Wishing you all the best. Thank you for having me. Thank you.